Hello. So I'm Will Larson, and I'm the VP of Platform Technology at SocialCode. No one knows what that means, including myself and my coworkers. So you guys think of me kind of a VP of engineering. What I want to talk about is building data infrastructure. And so I'm a manager these days. So I kind of think about things a little bit differently, and it's not until you talk to someone who hasn't thought as a manager that you realize how foreign your thinking has become. So when I think about companies, when I think about technology, when I think about Python or anything, I really think about growth and change and what it means. So we talk a lot about change in companies. So as you go from one office to 3 offices, 1 office to 3 times as many people. Talk a lot about having more products, go from 1 product, 3 products, 10 products, what happens there. But we don't always talk about what happens when your data changes. We talk a lot about scalability, going from one small database to a larger database to a different new database back to the old database and whatnot. But we don't necessarily talk about the social dynamics and how to scale a data platform in more of a kind of team-oriented way. So that's what I want to talk about tonight, is how do you build a platform where your team can grow with the data, not just from a technical perspective, but actually as people work. So what I wanted to do is I wanted to talk about where we started out, kind of the stack that we had, problems we had, how we had to solve them today, and kind of why we chose the solutions that we did. This should look pretty familiar to you. This is probably the most vanilla deployments you're ever going to get if you're running a Python infrastructure. And so it kind of goes like this. If you're running on Amazon, you have all your servers up there. You have a couple of web servers that are taking the requests from your clients. For us, we're running Django on Unicorn. Your servers are behind a load balancer. Got a nice big hosted MySQL cluster. Got a Redis, and then you might be doing some offline processing with Celery. So this is where we started. I think if you went to most Python startups, you're going to see something incredibly similar to this. And it works really well. Works incredibly well, but it starts to grow. And there's all sorts of interesting topics I love to talk about. How you grow different elements of it, how you grow the performance, how you grow the scalability, whether you go to kind of a service-oriented architecture. But there's also a lot of problems with the data that you run into relatively quickly. So 3 problems that we ran into and are pretty universal is that when you have a giant MySQL database, you run into a lot of schema problems. We work with Facebook and Twitter data, and one of the great parts of that is that they change their data constantly. And we have literally no control over this. And they push it out at convenient times, like Friday at 5 p.m., or accidental bug fix at 6 on Saturday that doesn't fix anything but breaks something else. So you can design a beautiful kind of schema. It's going to work really well. But if you're working with third-party data, it doesn't matter because you don't actually have any control over it. So one of the things that we've dealt with is as our database has gone from 1 terabyte to larger than a terabyte, is this. How do you run a schema migration when it takes 12 hours and you can't go down because you're running ads for clients and your clients don't really care about your database, don't really care about your platform, they just need you to run ads, or are you going to do a make good and then you're going to pay them back half the money that you made that day, then you're going to get yelled at. Another problem we ran into is not just literal data silos. So you have data silos sometimes where you have 3 different products and people aren't really communicating with each other, and you have a Twitter product and your Facebook product, you can't get the data together and your data scientists hate you because you haven't thought about how they need to work. But we've actually had data silos which are siloed just by the nature of the performance of the database itself, which is, so we get some new data, but our indices are so large. Our indices are already 80 gigabytes or 100 gigabytes. They can't actually alter the tables that are storing the indices to actually get at it. So you have all this great data, but you can't use it. And so your product becomes kind of horribly twisted over time in this way. And then another thing that has happened as you grow and you have kind of a single database is that you have a bunch of different users. You have an API that needs kind of real-time, up-to-the-second data. You also have a data science team who needs kind of high latency, high throughput solutions. You only have one database, and you don't really know what to do. So this was definitely us for a while. We suffered through a lot of it, and then we've spent a lot of time thinking about. And at the same time, we went from 1 office to 3 offices, from 1 product to 3 products, and from 1 database to about 20 or so databases. But how do we solve this problem? How do we make it so that we can share data in a pretty convenient way? So we thought about this a while, and these are the requirements we came up with. So first, we thought it was really important to decouple publishing and consumption. So what happens when you don't decouple publishing and consumption is each publisher has to know about the consumer, which means that you have a really high coordination cost. That means if someone else on the team wants to bring up a new server, they have to talk to everyone else who's publishing data, which means that they're not going to bring up a new server because they're not going to talk to everyone else on the team. They just get really slow, or you get really siloed very literally because everyone does everything else kind of on their own stuff. Another thing is we really wanted the ability to explore data cheaply. We have a very large data science team. And these are they're not developers, but these are people who are incredibly fluent with SQL. These are people who are much better than I will ever hope to aspire to be with SQL. But they can't write a great Python script. If their code goes into production, you have a meeting about how you screwed that one up. And you need the ability for them to query it pretty easily. Third, schema changes. As I mentioned, we don't have any control over our schemas at some level, so we need the ability to change really frequently, or we miss out on products to our competitors who can change their schemas more quickly. Finally, well, actually 4 is not finally if there's 5. Working on it. So something that we've dealt with before is it's fine if things fail. It's better if they don't fail, but when data solutions and core infrastructure fails, it needs to fail really loudly. And sometimes you run into experience where you all of a sudden are missing a month of data or 3 weeks of data, and you just can't get it back. I used to work at Dig, and we once had we set up our Hadoop cluster incorrectly. And the name tracker, the name node went down, and we lost every single piece of data for 6 months. So what would have been nice is if it had given us a visible error, or the person had not screwed it up. But instead what happened is it couldn't save the new config file to disk, so it just never did anything until it was restarted by accident months later. So failing loudly is really valuable. You don't really like to go talk to your board about how you lost 6 months of data. It's a little bit embarrassing. Then finally, kind of data store lock-in. There's all these sorts of new databases coming on, and every 6 months there's something new that's pretty cool. Like RethinkDB recently seems pretty awesome. Then like 2 years later, they actually work. And it's often 2 years later they work. So we didn't want to get stuck with MySQL. We didn't want to get stuck with Postgres. We didn't want to get stuck with Mongo or Cassandra. We wanted to have a lot of flexibility about how we could, as new databases come out, keep iterating, trying out new solutions cheaply. So this is what we ended up with. And it's, I've been told this is not the cleanest diagram, but I tried very hard. So when you start out on the left, you have services. And so if we go back here, this entire slide is one of these small little boxes in the services. So we have a bunch of services that are doing their own thing. Maybe one team's in Seattle, maybe one team's in DC, and they're just doing their own thing, not talking to each other. They don't need to. They're pushing data into a data input service. This is HTTP. We're using JSON schema to validate all the documents. One of the great failures of data warehousing is you can collect all the data but not have an easy way to validate it. And then you have all sorts of data you can't use, which isn't actually data. It's just kind of a pain in the ass. So we have all the data coming from all these different services flowing into this input and the data input, which validates the document, then accepts it. And then it pushes it into Kafka. And so Kafka, I think, is one of the most exciting databases I've worked with. I think if you go to the website, they call it PubSub reimagined as a commit log. And I don't know if that means a whole lot to you. It doesn't necessarily mean a whole lot to me. But next slide, I'll talk about why I think Kafka is probably the most interesting database I've worked with in a while, even though it's written in Java. Sorry, it's obligatory. So then we also use Zookeeper. We don't use Zookeeper because we are in love with Zookeeper, although Zookeeper is phenomenal. We mostly use it because it plugs in out of the box with Kafka, and it gives you some really great properties. Talk very briefly about Zookeeper. But the most important thing Zookeeper gives Kafka and also our input and output services is just coordination. The ability to kind of say, we have these consumers, this is what data they've seen. Talk a little bit more about that in a second. Then we also have kind of a shared data output layer. And what this has done is this has abstracted all of the consumers from all the inputs. And it's also abstracted all the servers and all the databases from the protocols and the storage layer in between. This means we could throw away Kafka, we could throw away Zookeeper, and we could switch to a totally new storage solution and all the services, all the backends are totally abstracted from it. And that's, again, an HTTP service where you can subscribe. But we also do some bulk loading into S3, which we can translate into Redshift and so on, which is a little bit annoying. So why Kafka? So I think, like I said, Kafka is the most interesting database data store that we've worked with in a long time. And it's a little bit peculiar. So if you start a new database, a new project, someone's going to say, I want to use Redis, because Redis is amazing. And I have a lot of love for Redis. I've used it a lot. And it's done some bad things for me as well. But the best feature about Redis that developers want to use, and usually say no if you can, is PubSub. So dead simple, you start it up, you can push messages in, you can have subscribers come and go, and it just works. And it just works as long as your consumer never goes down. It just works as you don't need to know if the data is actually there. It just works if you don't actually care about your data. And it just works as long as all the consumers can take all the data just as quickly as all the publishers are pushing them in. So really what Kafka does is it does PubSub write. So it decouples the speed of publishing from the speed of consumption. And the way it does this is data comes in and it writes it onto disk, and then each consumer has an offset. And the offset tracks how far each consumer has seen on a given queue, which means that you can have as many number of consumers as you want, and each consumer just has to have a single offset stored for it within Zookeeper. So very cheap, consumers come and go. If you screw up, you can set your counter back and replay data, and keep as much as you want for as much as you can afford. It also, the new versions of Zookeeper actually have replication. It's new in 0.8, which means it probably doesn't work, but we're testing that, and it works sometimes. I would wait a little while on that one. Another thing it gives you is horizontal or scalability, add more nodes, get more performance. Right now, you can, generally what they say is you will get to performance on I/O before you get to performance on CPU or memory with Kafka, and that's what we've seen even on network I/O, that is, not disk I/O. So even on Amazon, where the hard disks are usually pretty awful, we've seen pretty remarkable performance there. Finally, Zookeeper, a lot of new databases suffer with kind of distributed coordination problems. At Dig, we were an early adopter of Cassandra, which is now pretty stable, but at the time we adopted it, had a lot of flaws. It was just very early. We had a lot of flaws for adopting a technology that early for our production database. But Zookeeper just does the coordination really well. It's one of the thousands of implementations of Paxos. And it's solid, robust, just works. So one of the other things we did is we decided to use HTTP and JSON schema. You might say, why don't you use Avro? Avro is very similar to HTTP and JSON schema. And basically the reason we did is that we are a Django shop. We mostly use Django TastyPie. And it just was easiest for us to keep using technologies we're familiar with. So the input and the output services were actually implemented in Django using G-Event and Unicorn for some scalability there. Other thing is JSON schema gives you some really nice flexibility. You can dynamically load schemas off of a web server. You just put the URI in there, and that uses that schema to validate. And also you can have things like this, where you have a minimum or a maximum. And you don't usually get something like that where you can validate at that level with a schema for free. So, have our lives improved? And I would say yes, our lives have improved in a lot of really important ways. So the first thing we've done is we've been able to bring up a ton of specialized databases. We used to have this one monolithic MySQL database that we couldn't change. It had a lot of flaws. But now we have a bunch of smaller databases that have got 3 minutes, that just serve a specific purpose, and the team that needs it creates it. The team that needs it maintains it. So instead of having to go talk to a team across the country with a 3 or 4 hour time zone difference, just get the data out of the centralized store, bring up your new server, subscribe to the streams, and you're done. Also, it means that we've been able to move all of our data into a single data warehouse pretty easily. We've moved it all into Redshift on Amazon. And this flexibility of decoupling the consumption from the publishing meant that we didn't have to go talk to every team, get them to push their data in, just kind of worked out of the back. It's really not how that phrase goes. Run through it. finally, paradigm flexibility is that now we have the ability to kind of try a bunch of different approaches for different problems. So our data is on S3, we can run map reduces against it. Also from S3, we can push it into Redshift. But people want to try new technologies. We want to use Neo4j to see if that works well, if we could find a better way to do kind of replication stability there. And this gives us the flexibility to bring up new databases, actually load test them, test the performance without committing months or longer. I've seen years going to migration projects that don't launch. So it's been a pretty big improvement over our lives. And things we've learned, Kafka bindings in Python are not good. Don't use them. Don't plan too far ahead. We've radically simplified from what we started out with. That diagram used to be a lot more complicated. We've systematically cut more and more components out. Get up. Anyway, we'll just run with that one. And then the final one is that we initially wrote everything in Python and Unicorn, and that worked really well up to a certain point. But as we went from trying to do thousands of messages to tens of thousands, we just hit a scalability wall. That was related a little bit to Python and Unicorn, but a lot to do with just the bindings for Kafka in Python were very immature and had a lot of challenge getting G-event hooked all the way through. We had a bunch of Java developers on staff, and we actually just switched over to Java entirely for the entire stack. And that entire stack is a simple service that accepts documents and validates them, and a second service that kind of is a layer over Kafka. So it actually took us a couple of months to do that, to get up the performance level, but to actually just validate the concept took a couple of days. So I think one of the nice things about using HTTP as an interface, you can drop out, change languages, use the right tool for the right thing. Dev really wanted to use Erlang, which I love Erlang, but I don't love it that much. So now we will jump into questions. So you mentioned dumping data that doesn't meet the validation phrase during input. Isn't that a bit extreme? So it's an interesting question. We thought about this a lot. So the alternative to dumping data that doesn't validate well is that you push it into a didn't validate queue. And then you have another process which you can see the errors as that queue gets large, and then you can rerun kind of a corrected code or a migration code on it. It's interesting. I think what I felt and what the team felt was that by pushing things into that queue, you wouldn't fail loudly, you wouldn't fail quickly. Ultimately, the person who needs to fix the problem is the person publishing the bad data, and not necessarily the team maintaining like this shared piece of infrastructure. We felt this was a very violent but clear way to indicate that something was wrong to that person immediately. I think you could go either way, and it just kind of depends on the different dynamics you're looking for. I mean, there's social dynamics if you have someone who has to then go talk to the developers who are pushing bad data in and so on. That's a good question. So you mentioned that would be the same question. How did you feel about the level of DevOps required to go from your starting architecture to the last architecture? It's a great question. So we do all of our work in Chef. I wrote the first version of the Chef, so I'm pretty much happy to jump into the DevOps stuff. It wasn't too bad. We just spun up new nodes. The real pain that we had was configuring Zookeeper and Kafka to be fault tolerant and testing whether it was actually fault tolerant. We ran in, there are some dragons there, as they say. It's not perfect, but it was pretty reasonable. We do have a very strong tech ops team, and we were able to rewrite our infrastructure from the start in Chef. So it's all managed. We have all Jenkins builds. It's pretty standard, but it's pretty clean. So for us, it wasn't too bad, but I wouldn't want to do it and a bunch of other stuff at the same time. So yeah, I think does all data from the local data stores get pushed into the input channel? So I think there was a long discussion, mostly in my head, about what is data and what is kind of just stuff you put in a database. And I think they're different things. So basically what we decided is data is stuff that's actually meaningful and usually coming from a third party, unless it's convenient for it to not come from a third party. I would say this is kind of a problem that we're still working out. So you spoke of publisher-subscriber offsets. Yeah, so I can try to explain how SocialCode uses offsets, but basically you have a log, and in the log, I'll talk about 08. 07 is slightly different, but not in interesting ways. So you have a log, and you have a bunch of messages in it, and the first message is 1, the second message is 2, 3, 4, 5. For every consumer, you store which is the last message they have successfully received. And then as they get more messages, you increase that counter. You can say, give me 50 messages, and it'll give you 50 if they're available, and then you go from 5 to 55. And that's how that counter kind of decouples the publishing and subscription. Does that seem like that answers that question? I hope that answers that question, but feel free to ask afterwards, and I'd love to talk about it more. The last question. Oh, yeah, so if you're a Django shop, did you have any issues with South migrations? So there's a really excitingly helpful message in South, which is basically, you're using MySQL, go away. Which, it's not that funny. Yes, we have had a lot of issues with South. It's better than everything else we've used, but it's still pretty painful. So I'd love to answer any other questions if anyone has them. Thanks for letting me spend your time.